Dear friend, in this video I am explaining the concept of prediction. In case of data, when data is given to us, that is one case, and whenever data is available in terms of its statistics, that is given statistics case. So if we are having huge data and we would like to predict data which is going to be there in the next instant. So next instant, what kind of value data is going to take. If you want to predict the data in future, or if you are having data set and you want to predict the backward value of data or central value of data, this prediction technique they are used. So in case of prediction, we'll be having two kinds of data. One is we are having direct data which is available us for processing, and second case is given statistics case in which data is not available, its statistics is available. So how to go for prediction in both the cases, that is what we are going to see in this video. The prediction is divided into three types of predictions, or there are three different predictions are there. One is forward prediction, when data is given and we are going to predict the next value. Backward prediction, when data is given and we want to predict the backward value from the last value. And central prediction, we have past data as well as future data, so we need to find the central value. So data is known before the instant and as well as after the instant. So what is the data at particular instant, that we can also find out by using these predictions technique. The forward prediction with respect to given data case, and forward prediction with respect to given statistics case. Both the cases I will be explaining in this video. Now let us consider given data case. Data is given to us and we have been asked to predict the data in the future instant. What will be the data? Or it is also asked or it is also many times required when data is given to us and we would like to extract the features of the data by using some coefficients. So we say that is a feature vector or features of the data. So many times that kind of requirement can also be fulfilled by using this prediction technique. So let us see how this prediction technique can be used to predict the next sample and as well as to extract the features from the given data. So as I told you that there are three types of prediction. One is central prediction, then backward prediction, and next one is forward prediction. Forward. These are the three different predictions. Now I will be explaining in detail the forward prediction. So set of samples are given to you, and by using this set of samples you are predicting the next sample. So past, we are using past p samples. Let us say we are having n samples where n can be anything, and out of which I am taking past p samples to predict the next sample. So let us write that equation and see how we can have the prediction, forward prediction using given data set or given sequence. Let us assume that length of data or signal is n, where n is any value. Generally, if n is 10,000 or 20,000 or 1 lakhs, in that case your number of coefficients which are required to represent the data, they are of the order 10 or 15. With using 10 or 15 coefficients we can represent the huge data of, let us say, 50,000 to 1 lakh. So how to find these coefficients? That is our question. So we can say that these coefficients are nothing but the features of that collection of coefficients is called the feature vector. So let us see how we can find the feature vector, or how we can predict the next sample using past p samples. we are assuming that we have given n samples of the data, n is very large, and we are saying that using past p samples we can predict any next sample, right? So let us write the equation. E of n is equal to, this is the sample which we want to predict from its past p samples. K is equal to 1 to p. So we are having a1, a2, a3, ap. a1 into x of n minus 1, this is past sample. a2 into x of n minus 2, again it is past sample. ap into x of n minus p, again it is a past pth sample. So using these past p samples, I would like to find x of n. Then this second part, or this part, is called estimate of x of n. So while finding this estimate of x of n, I have to see that the error is minimum. So this is the error which is occurring when we are predicting x of n from linear combination of its past p sample. We are using past p samples along with coefficients a1, a2, a3 dash 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 ap. So our objective is find a1 to ap such that e of n error, that error is minimum. So this e of n is the error which is occurring because of prediction. So this is called prediction error. Prediction error. This is denoted by generally x cap n, which is estimate of x of n, which is estimate of x of n. So e of n is equal to x of n minus x cap n. So this is the equation. This is the equation, and this equation is I am going to use. Right, I am going to use this equation for finding the coefficients a1, a2, a3 dash 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 ap. Now let us expand this equation for different values of n and see that what equations, how many equations we are getting. Since we are having x of n, which is of length capital N, so you will be having definitely capital N samples with u. So x of n is of length capital N. So therefore we will be having n equations to find p coefficients. We are having n equations to find p coefficient. Let us find these n equations. So put the value of n and just expand the summation. You get first equation. n equal to 0, it is x0 minus, here if I put summation ak x of 0 minus k, and now if I expand this, it will be x0 minus a1 x of minus 1 minus a2 x of minus 2 and so on, minus ap here x of value of this n is 0 and k is p, so minus, it is minus p. So all the subscripts of x of n, they are negative except the first one. x0 is expressed in terms of linear combinations of past p samples. The x0 is the current sample, then definitely the previous next sample will be x of minus 1. So this is one equation. Likewise, for different values of n, we get n equations. Let us write E1, which is x1. Now here again ak x of 1 minus k. N value of n is 1. K equal to 1 to p. Here also k equal to 1 to p. Here also if you expand, x1 is the current sample. I am getting x1 with respect to its past P sample A1 x of 0 minus A2 x of 1 and x of minus 1 and so on minus AP x of 1 minus P. So this is the equation for n equal to 1. Similarly, we can write for n equal to 2, n equal to 3, n equal to 4 and so on. So last equation will be, since it is started from 0, the last equation will be e of n minus 1, which is x of n minus 1. Here the coefficients will be a1, and since I told you that here if it is x1 it is x0, so it is definitely x of n minus 2. And likewise if I go on, here a2 x of n minus 3 and so on minus ap x of n minus 1 minus p. Right? So I am having n simultaneous equations and I want to find a1 to ap. So here n is very greater than p. N is very greater than p. P is very small. So as I told you that maybe n is in terms of 10,000, 20,000 like that. N signal x of n may be speech signal, maybe ECG signal, maybe your time series, maybe rainfall data, maybe data from the stock exchange. So after having these n equations, now our objective is find the value of a1 to ap. So let us see how to find a1 to ap. Let us write this equation in terms of vectors. Right. Let us write this equation in terms of vectors and matrices. So and after that we'll see how we can solve this equation. So I hope you will remember all these equations, and I am writing this equation in terms of matrix notation. So the first column will be E0, E1, E2 and E of n minus 1. So the next here, our given data, there are n samples, so x0, x1, x2 and so on, x of n minus 1. So then comes the summation. The part of the summation, here part of the summation is written in terms of matrix and vector. So we are having here vector of coefficient a1, a2, a3, ap. Let us take only 3 coefficients. So corresponding to each of the x0, x1, x2, x3, there are past p samples. For x1, past p samples. X of n minus 1, past p samples. Just write for here past samples are x minus 1, x minus 2, generally first 2 and last. We have to write. So x of minus p. Here x1 is there, so next sample, previous sample is x0, x of minus 1, here x of 1 minus p. So now it is not necessary to write more than 2 equations and last equation. So here x of n minus 1 is there, so x of n minus 2, x of n minus 3 and last is x of n minus 1 minus p. Right? X of n minus 1 minus p. So this is a column vector, so I am denoting this by vector. This is another vector. It is a signal, given signal, so it can be written as in terms of vector. Then this matrix capital denoted by capital X. The size of the matrix is number of rows n and number of columns, they are p. And this A is again vector. Size of this vector is p cross 1. So now we have to see that our objective is to find this vector A. That is our objective. To find this vector A, what I will be doing here is I am using least square approach. Right? The least square approach says that your error should be orthogonal to your previous data. If error is orthogonal to data, in that case, whatever coefficient we get, they are called least square coefficients, right? And they are coefficient. They are based in these questions. So let us do that. Apply least square approach. apply least square approach to find A1, A2, E. A1, A2, A3, E. These coefficients. So we know that this matrix is having, this is first vector, second vector. So likewise matrix has p vectors. Matrix has p vectors. So matrix is, it is a, we can say it is a data matrix which is purely coming from your given data, and vector E is having E0, E1, E2, all these are errors in predicting x0, errors in predicting x1, error in predicting x of n minus 1. So we are having errors in, right here it is a vector, collection of error component is a error vector, collection of signal component is a signal vector. So this is data matrix which is coming from purely from data, and these are the coefficients which we are interested. Okay, so how these coefficients can be obtained, that we'll see with the help of least square approach. Least square approach assumes that the error is orthogonal to observation. So we are having observation. Observation is this matrix. This matrix is also called observation matrix. So matrix X is having vectors. Let us say vector x1 first column, vector x2 second column, and vector xp last column. So matrix can be written as collection of vectors. X1 is first column, x2 is second column, and xp is the last column. I am saying that this x1 and E, they are perpendicular, x2 and E perpendicular, xp and E, they are perpendicular. That is the least square approach. Least square approach assumes data is perpendicular to the observation. So what I am saying is inner product between error and this is error is E, and your this one this error is column vector, and now what I am doing is xi transpose, this is row vector multiplied by this E. So instead of multiply, what I can say is taking the inner product between error vector and column vectors of data matrix, and I am telling that I am assuming this error vector is orthogonal to x1, orthogonal to x2. So it means that I am doing this assumption. I am using this assumption. So by using this assumption, now what happens? What we'll do is we'll multiply this entire equation by x transpose, capital X. Capital X is a matrix, right? So x transpose, it is nothing, x transpose. What is this x transpose? X transpose is nothing but your this. These are all these vectors and transpose of individual vectors. x1 transpose, x2 transpose, and xp transpose. This is and entire transpose, x transpose. So this is x transpose, and now x transpose, it becomes a column vector, and in column vector each one is row vector. This is row vector of data matrix. It is first column becomes first row, second column becomes second row, last column becomes last row because of transpose. Now I told you that xi. So in case of this, we can write this is nothing but inner product is nothing but xi transpose E. This is the definition of inner product. xi, this is small xi, comma E. Small xi is vector. So this is the definition of inner product. X transpose of the first vector multiplied by E, error vector. This is the definition of inner product and standard inner product. So xi, E, all they are perpendicular because we are assuming least square approach. In least square approach, we assume that error is orthogonal to observation. So by assuming that, now I will take this x transpose here multiplied by vector E is equal to x transpose multiply this equation by x transpose. So x, now again x transpose, then x and vector E. So after having this equation, we can say that this is nothing but x1. Okay, if I multiply by x transpose and take the inner product, so what happens? If I take inner product, here, or if I say only multiply, let us just see it is multiplied. X transpose E. What happens? X transpose E. X transpose is what? Actually, X1 transpose, X2 transpose, XP transpose, and multiplied by E. E is a vector. So multiply by X transpose. Then in that case, what happens? You get a zero vector. Vector, okay? This first vector multiplied by this, you get 0. Second vector multiplied by this, 0. So likewise, this inner product with this and this multiplied, this and this multiplied, this and this multiplied, the result will be a 0. So in that case, what happens? It is here. If you assume least square approach, so error is orthogonal to the data, given data, and here X transpose X A. Now our objective is find A. So take this towards other side. So we can write A is equal to X transpose X inverse. X transpose X inverse. This, okay, A is taken to this side. Whatever was multiplied this, it has come to this side. X transpose. So this is the formula. If we use this formula, you can easily find out coefficients A1, A2, AP. Now using these coefficients, you can have a model which will generate this entire data. Let us see how you can do that. So A is known to you, means A1, A2, A3, all those things are known to me. So I can write this is x of n minus AK, x of n minus k. After having A1 to AP with me, right, and error is minimum because of least square approach. So here I can write B0 multiplied by x of n, where B0 is 1, and here I write BK x of n minus k, where BK is equal to x of BK equal to minus BK equal to AK, and B0 is equal to, let us say, 1. B0 equal to 1 and AK equal to minus BK. By taking this assumption, then that equation can be written as E of n is equal to summation BK x of n minus k, k is equal to 0 to p. Because k equal to 0, this term is coming B0, B0 x of n, and rest of the p terms, they are as it is, only to adjust minus sign and just taking notations BK. Now if you observe this equation, so what happens by observing this equation? It is nothing but convolution of B of n with x of n. So this is E of n. So from this prediction, we are finding the coefficients of the predictors. The predictor is a pth order predictor, because we are finding the next data using past p samples. That is why this predictor is called pth order predictor. Pth order predictor. We are using past p samples, and that is why we are having p coefficients. So because of that, we are saying it is pth order predictor. But this pth order predictor, after writing in this form, it becomes a linear filter. So let us see how it is seen as filter. So see, x of n is passing through B of n. B of n is a filter whose coefficients are B of n. If you write, you will understand that it is B0, right, minus A1, minus A2, and minus AP. These are the coefficients of Bn. So whenever here now it is, see, whenever x of n is passed through a system B of n, we are getting E of n, where E of n is minimum in least square sense. So here whatever we are getting in error, the error is not carrying any information. Whatever information present in the signal, it is absorbed by the system. It is absorbed by the system means that information is available in the form of coefficient, system coefficient. System coefficients is extracting the information which is present in the signal x of n, and we are getting u of n. So u of n is minimum in least square sense. So here, by observing this, we can say that signal, whenever I am having signal x of n, and if I pass that signal through a system Bn, I am getting error which is minimum in least square sense. So entire information present in the signal is available in the system coefficient. System coefficient, they are carrying the information. They are carrying the information of the signal. So whenever you want to send a signal, let us say signal is having 20,000 samples, let us say, then instead of sending the signal, what you can send is, you send Bn, just p coefficients, p plus 1, rather 0, that 0th coefficient is also there, b0 is 1. So p plus 1 coefficients for 10,000 samples, we can have, let us say, 10 coefficients. So if you send these 10 coefficients to us receiver side, and receiver side, if it is having inverse filter, which is just inverse of b, we can extract the signal directly. So what I am saying is, if I have a receiver, in that case receiver whose transfer function is 1 by b of z, and which input is e of n. E of n is the error signal, and which is carrying very small information, right? So by transferring this e of n to the receiver and some coefficients, most of the values of u of n here by 0. So taking enough care of that, if you will send this e of n and coefficients of filter, that is b of z, we can get the signal, we can generate the signal back. So this is what linear prediction, and that is on top of it is forward prediction. Forward prediction means we are predicting the next sample from the past p samples. So this is pth order predictor, pth order forward predictor. So whenever we are having this one data, rainfall data, and we want to predict the next year data of rainfall, so we can do that by using all previous year data and take their linear combinations. So we can do the prediction. So this is one step prediction, two step prediction. Whenever I am predicting x of n plus 1, so n plus 2, two step predictor, three step predictor, like that we can do, and we can predict the coefficients. We can predict the next sample or next to next sample, and at the same time we are taking care that error is minimum. So this is all about linear prediction, and that is for the given data case. Now let us see the same example, or same instead of example, let us say prediction, forward prediction technique, when data is not available, but we have given the statistics of the signal is known to you, okay, and data is not available, we are not having access to the data. So signal is random. If signal is random, so we don't have access. If we have access, then it is deterministic. So if you know the samples of the signal, if you know amplitudes of the signal, nothing random about it. So if we are having random signals, in case of random signal, we can talk about its correlation, we can talk about its PSD, and we can talk about its other parameters, but we don't have that signal in terms of amplitude in our time domain, or let us say any other parameter. Okay, so that is the this one about forward prediction.